Well, today we want to finish our section on solving trigonometric equations. This is actually one of the harder sections of the book. There's a lot of material here, that's why we only did part last time. This first part will be a review of what we did last time. For instance, here's the simplest case, solving a problem where its trig function equals a number. If its trig function equals a number that comes from the unit circle, we can solve it exactly on the unit circle. We simply make the sketch of the unit circle. If you have sine of an angle equals a number, you simply remember that sine is the y-coordinate. You draw all the points y equal that number. Here's the horizontal line, y equals a half. And then that tells you what terminal rays are possible to give you sine theta equals a half. They have to go through one of these 2 points, or you wouldn't have the y-coordinate equal a half, hence sine theta not equal a half. So there's only 2 possible terminal rays, that one and that one, to make the sine theta equal a half. Now, if you're solving it for theta arbitrary, there's an infinite number of solutions. Let's do the ones between 0 and 2 pi. First, we have this angle here. What is it? We drop the perpendicular. Since y is a half here, this side length is a half to get up there. This is 1 because it's a unit circle. The Pythagorean theorem, if you calculate it, would force this one to be square root 3 over 2. And this is a 30-degree angle. Let's do this one in degrees. On all these problems, there's a symmetry. By symmetry, since this one also goes up a half, this one also has to be 30 degrees. There's exactly 2 angles between 0 and 360 degrees that will have the sine equal a half. It's just this one right here. Theta equals 30 degrees. Or this one, where I take 180 back up 30, is 150. 2 solutions exactly in 0 to 2 pi. Now, if I have a problem like this where I ask for any angle theta, then you say all the other angles still have to have these 2 terminal rays. What are they? They're all the coterminal angles. You can add any multiple of 360 degrees to either of these. So let's write it that way now. It could be 30 degrees or 150 degrees. Let's write this in white. 30 degrees or 150 degrees plus a multiple of 360. K times 360 degrees, where k is any integer, 0, 1, minus 1, 2, minus 2, etc. Here's your answer. Theta is one of that infinite list of angles. That's how you solve sine equals a number. You say sine is the y-coordinate, draw the y equal that number and find the terminal rays, use those to find all the angles. What if we have something else like secant theta equals square root 2? This one, if you have a sine or a cosine, you can use x or y coordinates, but if you have secant or cosecant, you first write the reciprocal. Rewrite this as 1 over cosine equals square root 2. And then take reciprocals. Cosine theta equals 1 over square root 2. What does that look like? Let's try the unit circle again for this one now. If we have cosine equal a number, remember cosine is the x-coordinate in the unit circle. So I go out to 1 over square root 2 about here. And if I'm going to get that x-coordinate, here's the line of all x-coordinates, x equals 1 over square root 2, is a vertical line. There's exactly 2 places where this intersects the unit circle, hence exactly 2 terminal rays that can make the cosine equals 1 over square root 2, right? To get cosine 1 over square root 2, you take a terminal ray, drop a perpendicular, and it has to land at 1 over square root 2, so these are the only 2 terminal rays. If I want all angles between 0 and 360 degrees, now I notice there's one here, and I just keep going all the way around until I get back here. There's this one here, and there's this one here. And that's it. So I conclude then that theta equals this angle. What's this? Well, it went over 1 over square root 2 on this side to get x equals 1 over square root 2, right? And it's 1 on this side. I recognize this is a 45, 45, 90 triangle. The Pythagorean theorem would force this to be 1 over square root 2. Hence, this has to be 45 degrees here. And by symmetry, then, this has to be minus 45 degrees going this way, or let's draw it this way and call it plus 45. So this angle all the way around here is 360 back up 45 is 315 degrees. So there's two answers to this one. Theta equals 45 degrees or 315 degrees if I ask you between 0 and 360 degrees. But if I don't put a stipulation, I just write it like this, then you add any multiple of 360 because those are all the coterminal angles, all the angles that have these same terminal rays. So 45 plus k times 360, 315 plus k times 360. There are all the angles that have secant. I'm going to just erase my next problem. Secant equal square root 2. Finally, if we have a tangent problem, that's the hard one. Here was part C. If I want the tangent, for instance, equal minus square root 3, tangent isn't x or y, it's y over x. Tangent and cotangent are the hard cases. So I write minus square root 3 as a quotient, minus square root 3 over 1. Now, if only this is y and this is x, it can't be because that's outside the unit circle. Square root 3 is bigger than 1. This is already 1. That's a point outside. It can't be y and x. The way you make it an xy point on the unit circle is you root some square of these. Minus square root 3 squared plus 1 squared is square root of 4 is 2. And you divide top and bottom by that number. Now, this could be y. And this could be x because this will be on the unit circle. When you divide by the root some square, then this square plus this square will always be 1. So it's a point on the unit circle. Or, it's not the only point, I could take the minus on the bottom. I could put plus square root 3 over 2 on the top and minus a half on the bottom. This could be y and this could be x. This gives me two angles for the tangent. When I sketch the unit circle here, I can have y equals square root 3 over 2. This one is almost a 1, right? It's like 1.7 over 2. And minus a half for x. So it'll be about this point here. The other one is always the opposite direction. 1/2 over and square root 3 over 2 down. We'll go right there. What is this angle? Well, again, you say the coordinate I see is square root 3 over 2. If I drop the perpendicular, this is 1/2 here. This is square root 3 over 2 here. And this unit circle, this is 1 here. I know this is a 60-degree angle. So this angle must be 120 less 60 is 180 less 60 is 120 degrees. Then I can take any coterminal angle by adding 360 over and over, so it's 120 plus k times 360. Those are all the angles that have this terminal ray. But this one here, well, these are always opposite each other for tangent and cotangent, so we'll take 120 plus 180, right? 120 plus 180 makes this one 300 degrees. And then I could add k times 360 degrees. So this is all the angles that satisfy, oh, I did this wrong. Tangent equals square root 3 plus square root 3. No, that's right, sorry. Minus square root 3. There's a trick though. This is not the simplest way to write it. When they're directly opposite each other, you can do the following and say, wait a minute, I can take this angle plus 180, plus 180, plus 180, plus 180 instead of doing 360s. Right? Instead of doing this, I could say instead, either of those angles, let's take the smaller one, 120 degrees, and add k times 180, and this takes both sets of angles in. this is the better answer. This one's right, this one's better, right? So that's the review of solving trig function equal a number. Here's the second method we have. If you have a number a times the trig function of theta plus b equals 0, we could just subtract b and divide by a, then we get trig function equals a number and can solve it. Let's try this one. If I have a number times cosecant theta plus a number equals 0, let's write that equivalently by subtracting 2 and dividing by square root 2. As cosecant theta equals minus 2 over square root 2. Well, we could simplify that. This is actually minus the square root of 2, but rather than doing that here, I'm first going to turn this thing over. I have to anyway. Remember, when you want to solve secant or cosecant equals a number, you first take the reciprocal. So I'm going to write this equivalently. Taking the reciprocal to the left is sine theta must be equal to the reciprocal of the right, minus square root 2 over 2. Now, when I have sine equal a number, I say sine is the y-coordinate, and I appeal again to the unit circle. I draw the line, y equals minus square root 2 over 2, that's about minus 0.7. I observe that there's exactly 2 points in the unit circle that have that y-coordinate. Here's one, here's another, there's here and here. We need then 2 possible terminal rays. What angles are they at? Let's solve this one for theta between 0 and 2 pi. Let's use radians. And just restrict ourselves, not take any angles, but just within one rotation, 0 and 2 pi. Well, what angles are these? If this is y equals minus square root 2 over 2, it follows that this distance here is plus square root 2 over 2. This is 1 because it's a unit circle. That makes this, by the Pythagorean theorem, you will force this side equals square root 2 over 2, and this is a 45, 45, 90 triangle. Follows that this must be an angle 45 degrees, or pi over 4 radians. Let's write that chalk you can see in the camera, hopefully. So evidently this angle here is 180 plus 45, or pi plus pi over 4. Is 5 pi over 4, right? Pi over 4 and pi is 5/4 pi. Now this one here, the easiest way to do that is say, oh, it's 2 pi, a whole rotation, less this one by symmetry has to be equal to this one. So 2 pi back up pi over 4 is, well, let's see. 2 pi is 8 pi over 4, take away 1 pi over 4 is 7 pi over 4. Alright, 8 pi over 4 minus pi over 4. There's my 2 answers there between 0 and 2 pi. Next thing that can happen, you could have a trig function equal a number, or a times trig function plus b equals 0. And instead of having the trig function of theta, have trig function of 2 theta, or 3 theta, or 4 theta. How can you solve that when it's not theta in there? It's a little trickier. But what you do is you just start by substituting u equal k theta. Or in this case, u equal 2 theta. So this is kind of like a cookbook, and we're going to run down the methods here. When you see this, you do this. When you see that, you do that. It's just like when you bake a pie or something. You put in this ingredient, then you put in that one, you cook it at that temperature and so forth, right? So we're following a cookbook-like thing here. When I see this, first thing I'll do is let u equal to that and make it a problem of the other kind. Look what happens. Now this is cosine u equals minus 1, and I can solve it by my first method. Cosine is the x-coordinate of the unit circle. So when I draw the unit circle, I draw all points, or I draw the vertical line, the line x equals minus 1. Here it is. It just grazes the unit circle. We say it's just tangent, right? At minus 1. And that means that there's only one point on the unit circle that has cosine u equal minus 1. It's therefore this terminal ray, and it must be theta equals pi. Let's again solve this for 0 less than or equal to theta less than 2 pi. One once you've solved these problems between 0 and 2 pi, all you have to do to get all the rest of them is just add 2k pi. That's k rotations. So we'll solve it this way and just recognize if we put a plus 2k pi, then it's the other case where you want all solutions. Alright, so there's only one angle this time between 0 and 2 pi. It's this one here. We start here and go around. We hit one terminal ray, that's it. So theta equals pi. Up, not theta, it's u, right? U equals pi. Where u was 2 theta. Now here's the trick. That looks like theta equals pi over 2 is the only solution, but it's not, right? Even though we're not looking for all solutions, we will initially try and find all solutions and then throw out the ones that aren't between 0 and 2 pi in this problem. Because actually, when theta goes between 0 and 2 pi, u being 2 theta goes between 0 and 4 pi. So we can either check 0 to 4 pi or just find all the solutions and throw the extras out. That's what I'm going to do here. The reason being, if it's 3 theta, then you got to figure out now it's between 0 and 6 pi. This way you never have to figure it out. Just find all the solutions, throw the ones that you don't want. I think it's easier. 2 theta equals u is pi plus 2k pi. That's k additional whole rotations, where k is any integer. So this is all solutions, theta, not just the ones between 0 and 2 pi. Now I divide through by 2 and get theta equals, I have to divide the whole side by 2. It's pi over 2 plus 2k pi over 2 is k pi. So those are all solutions. Now we want solutions theta between 0 and 2 pi. Well, we try k equals 0 and we get pi over 2. That's 1. Theta equals pi over 2. Then we try k equals 1. We get pi plus pi over 2. That's 3 pi over 2. That's another one. But if I put k equals 2, it's 2 pi plus a positive angle. It's too big. If I put k equal minus 1, that's minus pi plus pi over 2 is less than 0. That's too small. It must be that this is all solutions right here. Pi over 2 and 3 pi over 2 are 2 solutions to the cosine 2 theta equals minus 1 problem. When you have a trig function of k theta instead of theta, just substitute u equals k theta. There's the cookbook solution. Well, there are lots of harder equations and trig functions that we can solve. This is a real common one. Once you get this one, you can kind of see how to do the even harder ones. But suppose I have a times the trig function squared plus b times the trig function plus c equals 0. Can I solve that? That looks really hard. Well, you can if you just substitute u equals the trig function. It turns it into a quadratic equation. And you can solve that by algebra, either by factoring or by the quadratic formula. Remember both of those? So here's a good equation. Sine squared plus 2 sine theta equals 3. Boy, that looks difficult, doesn't it, with the square in there? Once you see the square, think quadratic formula. This is not in the right form, though, right? I want 0 on one side to apply the quadratic formula, or factoring. So first I'm going to get 0 on one side and say this is sine squared theta plus 2 sine theta minus 3 equals 0. Now, once 0 is over there, I can factor a lot of the time. If I can't guess the factors, then the quadratic formula always works. I'll make the substitution, u equals the trig function, rewrite this by putting u equals sine theta as u squared plus 2u minus 3 equals 0. Look, a quadratic equation. We can solve that easily, right? Let's try factoring. Factoring is faster when it is possible, but sometimes it's too difficult to guess the factors, and you have to apply the quadratic formula. And there's some actually that don't factor, but we won't be doing those. They won't factor with real numbers. All right, so the trick on this is to think of how did I do algebra, right? Blank times u plus blank times u plus blank equals 0 is the way I'm used to it. If you're used to factoring it slightly differently, that's fine. Do what you did in algebra, right? That you know how to do. Now what goes in these blanks, you recall, has to have product equal of a lead coefficient, 1 in this case. So this product here equals 1. And what goes in these blanks, you recall, when you FOIL this out, right, this time this gives the u squared term, so the product of these has to be 1. when you FOIL it out, this times this plus this times this plus this times this plus this times this, the only one that gives you just a number is this times this. So this product is minus 3. So product equals minus 3. So what can I put in here? I'm going to put 1 and 1 in here. I could put minus 1 and minus 1 also, but then I can pull the minuses out and cancel them, so there's no point. So I'll put 1 and 1 here. Then in here it has to go either minus 1 with plus 3 or plus 1 with minus 3. That's my only choices for integers, which is the only thing I'm going to be able to guess to go in the blanks. So let's try minus 3 and plus 1. I can put, or plus 1 and minus 3, doesn't matter the order. And try FOILing it, see if that works. This is u squared minus 3u plus 1u. Oh, it's minus 2u. That's wrong. So I'll try putting the minus here and the plus here. Now I've got this times this is u squared. Just FOIL to check. First, outside, inside, last. You take first, outside, inside, last of the products. First is u squared. Outside is 3u. Inside is minus 1u. Last, this times this is minus 3. Just taking all possible products of pairs here. And these come out to be 2u. Sure enough, u squared plus 2u minus 3 equals 0. I've factored that out. I might get rid of some of the clutter here and write this as u minus 1 times u plus 3 equals 0. Now I know from algebra the solutions to that, right? You have the zero product property. The product of two numbers is 0 if and only if at least one of the numbers is 0. So either this number is 0 or this number is 0, it follows that either u equals 1, so that this number is 0, or u equals minus 3, so that this number is, this factor in the product is 0. Right? Factors are things that are multiplied together. So we call each of these a factor. So u is 1 or u is minus 3. Those are the only solutions. But wait, we wanted theta, not u. U was sine theta, so we see that the original equation is completely equivalent to sine theta equals 1 or sine theta equals minus 3. That's the only, right? All these were equivalent if and only if statements. Well, how can sine theta be minus 3 if you draw the unit circle here? Sine is the y-coordinate. Here's minus 1, minus 2, minus 3. That's a long way down here. It doesn't intersect the unit circle at all. There's no solution. You should recall that the sign of any number is a number between minus 1 and 1. It can never be negative 3. So this always has to be between minus 1 and 1, or the horizontal line won't intersect the unit circle. There's no solution. So we can scratch out this one. The original is equivalent to just this alone. Sine theta equals 1. Sine is the y-coordinate. So we look on the unit circle, and we draw all points y equals 1. We observe there's only one point on the unit circle with y equals 1. Hence only one terminal ray. Hence we have this angle here between 0 and 2 pi is pi over 2. I didn't restrict theta this time, so I'll say all solutions are theta equals pi over 2, that 1. That's right here. And any coterminal angle, you can add 2 pi, you can add twice 2 pi, you can add 3 times 2 pi. You can add in general k times 2 pi, which we usually write by convention as 2k pi. So there's all the solutions to this one. Well, these are just getting harder and harder, aren't they? I told you this is one of the harder sections of the course. So try these. There's no substitute really for practice. Ice skating, I like to use that example. Seems so hard when you first go out there, keep falling down and falling down. But once you're used to it, it's really easy, and so is this stuff. It's just a matter of practice till you just look at it and say, oh, I see, it's this kind. What about this kind here? If I have more than one trig function, my rule is try one of these two things. I'm going to try to rewrite in terms of one trig function by using trig identities, or I might write it as a product of two trig functions equals 0, each factor having only one trig function. So let's try this one here. What can I do with that? There's a sine and a cosine. I can't solve it by any of my other methods. But I remember the Pythagorean identity. Sine squared plus cosine squared equals 1. Solve for, right, this one. if I subtract cosine squared, I observe that sine squared is equal to 1 minus cosine squared. I can make that substitution in here and rewrite this equivalently as twice 1 minus cosine squared minus cosine equals 1. There it is. Now I've got one trig function. I try and fall back to one of my other techniques. Remember the house that Jack built, that famous story? That's kind of what this is like. Anyway, something built this, we have to go back to it. If we multiply this out, we got 2 minus 2 cosine squared theta. Alright, multiplying this out, minus cosine theta equals 1. And I can subtract 1 from each side and rewrite this as minus 2 cosine squared theta minus cosine theta plus 1 equals 0. I just subtracted 1 from each side and rearranged the terms. A cosine squared plus B cosine plus C equals 0. That's a technique we already had, right? So remember these procedures for equations with more than one trig function. These are all rules of thumb to deal with the kind of equations that typically come up in industry and science and so forth. This is not an exhaustive list. These are the things that commonly work. Sometimes you'll see another method that works. By all means, go ahead and use other methods too. There are some problems that are just difficult. They'll fall to any of these techniques. So we're not going to be able to solve every trig equation. We're going to learn some common techniques for solving common things, much like in ice skating. You learn common moves to do certain things, but somebody always comes up with a new something or other, right? Here's our first equation that we were solving. We can rewrite it like this. Well, let's see. Maybe we can factor that. I haven't illustrated the other method. Instead of trying to factor it, let's try the quadratic formula. Let's rewrite this time letting u equal cosine theta. This will become minus 2u squared minus u plus 1 equals 0, a quadratic equation. By algebra, I can try factoring, or I can use the quadratic formula that takes a little longer, but it always works. So I say u equals, if you have au squared plus bu, b is minus 1, plus c equals 0, I get minus b plus or minus b square root b squared minus 4ac all over 2a, and those are the solutions always. If you get a square root of negative, that means there is no solution. And it's telling you that too. So minus b is plus 1, and then plus or minus square root of b squared minus 1 squared is plus 1, minus 4 times a is negative 2, times c is 1, all over 2a, and a is negative 2, 2 times negative 2. Tells us, let's see, 1 plus 8 is 9, square root of 9 is 3. So 1 plus 3 over negative 4 is 4 over negative 4. Or 1 minus 3, choose the minus sign, is negative 2 over negative 4 is 1 half. Negative 2 over negative 4. And so this is either negative 1 or 1 half. Two solutions to this for u. If that's u, now what we want to do, actually we want to find out, since u is cosine theta, we're looking for what is theta. So this is equivalently cosine theta is negative 1, or cosine theta is a half. Now, cosine theta equals 1, we can solve on the unit circle. Cosine is the x-coordinate, so we draw the vertical line, x equals, oops, wrong one, x equals negative 1. And observe there's only one terminal ray going there. We also want to solve cosine theta equals a half. x coordinate equals a half. Leaves us two angles, this one and this one. What are those? Well, if this is a half out here, then it's half on this side of the triangle, one on this side. This must be square root 3 over 2. The Pythagorean would force that. Once you see two of the three sides of a special triangle, and when you memorize, you know the third side automatically. This must be a 60-degree angle. Let's solve this one in degrees. Let's say that's 60 degrees. Then this one is 360 back up 60. By symmetry, this also has to be 60 degrees. So there's two solutions, 60 degrees or 300 degrees. And then this one here is 180 degrees. What we have for all our solutions now is theta equals 180 degrees. And if we're not restricting to be between 0 and 360 degrees, we have plus k times 360. And then we have 60 and 300 degrees also. 60 degrees plus k times 360. And 300 degrees plus k times 360. There's all solutions to this equation. Pretty tricky. How about this one over here? Suppose I have 5 sine 2 theta minus 3 cosine theta equals 0. I have two different trig functions and two different angles. Always get one angle. So get one angle, that's the first thing I think you should do. I could write that as step 6. One of these is a multiple angle, the other is not. But get one angle always. Let's rewrite sine of 2 theta by the double angle identity is 2 sine theta cosine theta. Now, how can I solve this one? This one is really difficult. I don't see a trig substitution to get this down to one trig function of theta. I should call this 10. 10 sine cosine minus 3 cosine equals 0. We're going to use the second strategy. If I factor this, I notice there's a common factor of cosine. I could rewrite this as 10 sine theta minus 3 times cosine theta equals 0. So this has two different factors. This factor has only sine in it. This factor has only cosine in it. We can solve this by the zero product property. For a product of factors to be 0, either this one's 0, 10 sine theta minus 3 equals 0, or this one is 0, cosine theta equals 0. Those are the two possibilities. The first one says by adding 3 and dividing by 10, sine theta could be 3/10. Now let's solve this one again for theta between 0 and 360. And this one will be cosine theta equals 0. One comment, a lot of students will write this. This makes perfect sense, say the solutions are these and these together, but the word and in mathematics technically means that theta has to satisfy this equation and simultaneously this one. And there's it's not what we mean. We mean it satisfies one or the other or both. We use the word or because and means it has to satisfy both, and that's not what we mean here. So if sine theta is 3/10, what's the solution to that? We haven't talked about that yet. When this is not a number that comes from a special angle, what you simply do is solve on the unit circle like this. Say, once again, this is the y coordinate equals 3/10, so I'll put y equals 3/10. And I notice there's two angles, but I can't tell you the angle by heart. Instead, I know this. I know that this one is the arc sine. One solution of sine theta equals 3/10, or any number between plus and minus 1, is theta equals the inverse sine. Which angle is it? Is it this one or this one? Well, the inverse sine always gives you an angle between plus and minus 90 degrees, plus or minus 5 or 2. So we're we're gonna say it has to be this one. This one isn't between plus or minus pi over 2. This is the one that's the arc sine. What could this one be? By symmetry, right, we went up the same height. This one here must also be the arc sine of 3/10. So we observe that one solution is theta equals the arc sine, the other one is 180 degrees minus the arc sine. So theta equals 180 minus the arc sine given in degrees. Be careful, your calculator's in degrees mode. When you evaluate arc sine within radians mode, it will give you the radians measure of the arc sine. If you evaluate it in degrees mode, it will give you the degrees measure of the arc sine. So these are the two solutions to the first equation. But we also have one more, cosine theta equals 0, that's x equals 0. That's this unit circle. And for x equals 0, that's this vertical line, right? There's two terminal rays there, this one and this one. We observe that theta can be pi over 2, 90 degrees. Or it could be this one, 270 degrees. And that's it for theta between 0 and 360. So in all, we say therefore, 3 dots mean therefore. Theta is the arc sine of 3/10. Let me get rid of the original problem. It's getting in the way. Theta could be the arc sine of 3/10. It could be 180 minus the arc sine of 3/10. It could be 90 degrees. Or it could be 270 degrees. 4 different angles for this one, between 0 and 360 degrees. If I ask you for all angles, you just put plus k times 360 in each of these and you'd have all angles. Well, let's try those, see if you can do the homework. This kind is pretty tough. We should do one more example of that. Well, here's the last example for today. This is most of the common methods that people use. We can write harder equations, but they mostly use the same rules of thumb. So let's try this one. Again, suppose that we want to solve a trig equation and we don't get special angles, so we have to leave the answers in terms of inverse trig functions. Often what you need in real life is to use decimals, right? If you're a surveyor, you just put 27.8 degrees or something, or if you're an astronomer, you might use degrees, minutes, and seconds, but you won't write these things in terms of, won't be able usually to write these things in terms of special angles. You'll have to use some sort of approximation, such as 2 decimal places. Let's try that here. Suppose I want to solve 2 secant theta minus 3 equals 0. You think back, which Cook-Buck technique applies? It's not an A secant squared plus B secant plus C equals 0. It's not one of those. There's not a multiple angle k theta. There's not more than one trig function. It's very simple. It's just A times trig function plus B equals 0. I go back to my method 2 and I simply add 3 to each side and divide by 2 and I get secant theta equals 3/2. Right? Trig function equals a number. When you have secant or cosecant, you immediately write the reciprocal equation. The reciprocal to the left, cosine theta, is the reciprocal of the right, 2/3. This we know doesn't come from a special angle, right? If we see square root of 2 over 2 plus or minus, or 1 plus or minus, 0 plus or minus, 1/2 plus or minus, square root of 3 over 2 plus or minus, that's from a special angle, but this one's not. So how do I get that? I just have to solve it on the unit circle for all the angles. If cosine is going to be 2/3, cosine is the x-coordinate, so I draw the vertical line, x equals 2/3. Observe that there's exactly 2 points in the unit circle with that coordinate. Hence, only 2 angles whose cosine is 2/3. What angle is what? Well, what's that one? We know one solution is the inverse cosine. Is it this one though, or is it this one, or maybe it's this one, or the inverse cosine, right? One solution is theta equals the inverse cosine of 2/3. As long as this number is between plus and minus 1, there is at least this solution. Remember, the inverse cosine gives you an angle between 0 and pi. Let's solve this between 0 and 2 pi. So it can't be this one or this one. It can only be an angle in here. It has to be this one right here. This one must be the inverse cosine of 2/3. So what's this angle? Exactly, it's 2 pi back up. By symmetry, this angle here is also the inverse cosine of 2/3. How do you know that? This is 2/3 over here and on both triangles, and 1 on this side. They're congruent triangles, right? This triangle has 2 sides the same as the right triangle. This has 2 sides the same as the right triangle. They'll actually have all 3 sides the same. If this is the arc cosine of 2/3, this is also, because it's congruent triangles. Now, if that's arc cosine of 2/3, this angle is 2 pi back up arc cosine of 2/3. So there's 2 answers exactly: arc cosine of 2/3 or 2 pi less arc cosine of 2/3. Exactly, but in the real world, it's shooting a rocket up. You want to know how to measure the degrees on the dial. You put in a decimal approximation. So approximately then, we'll say on this one, the arc cosine of 2/3 is 0.84. If you run your calculator, 0.8410 blah blah blah. Let's put it's equal to that if you carry out all the decimal places. That's by running the calculator. Make sure it's in radians mode or you'll get a big number, then you'll know it's wrong, right? So we'll round this and say it's approximately 0.84, because 2 decimal places means march 2 places, 2 digits to the right of the decimal point. And if the third digit is 5 or greater, you round this up. If this is 4 or less, you leave it the way it is. So we write 0.84 as the approximation. Now over here, 2 pi minus that is, you have to write 2 pi, it's 6.28 blah blah blah. Now we subtract 0.84 blah blah blah. Let's see. So we come out with 5.44, I guess. So rounding to 2 decimal places, I left off these other digits. You have to make sure that when you subtract, you don't have to round that separately. All right, that's it. Try all these problems in this section. Like I said, what it really takes is practice, but they're all fall into one of these techniques.